All right. Hello. Welcome back to CS50. This is the end of week 7. So we've got a lot of fun stuff ahead. I thought we would wrap up a couple of the lower level details that we began on Monday today, but really focus today on some techniques and some concepts that you'll be using certainly throughout the remainder of the semester, albeit in a completely different context of web programming. And then if you ever pick up a computer and a compiler or a text editor in the future, odds are these same concepts will recur for quite some time. But first, do you mind bringing the house volume down a bit? But first, a few comments toward an end of teasing you with some ideas for your final projects and also to get the juices flowing with regard to final projects. We'll spend more time on this next week or so. We'll release the specification for the final project, even though it's not due for a couple of months, so that as you dive into the web-based aspect of the course and the web-based P-sets, you start to at least think about the kinds of things you might want to do, but realize you need not implement something web-based. You're welcome to do most anything, as you will see. So we surveyed all 1,600 plus students that ended up using this particular tool to shop for courses this past fall. We set an arbitrary date of releasing some updates today because you guys, if you've not heard, have to do this thing called pre-term planning starting this year, which means registering what you are likely to take so that FAS can plan teaching fellows and room assignments more effectively. If you have no idea what I'm talking about, you odds are have some email in your harvard.edu email account somewhere, so go dig that up. I think the deadline's in a couple of weeks. But we wanted to use this as an opportunity to make this tool even better and to actually practice what we're preaching, take in feedback, and try to iteratively improve the design of this thing. So now if you've never actually used the site, it's hopefully pretty straightforward. You go to courses.cs50.net, and the purpose in life of this application is really just meant to make navigating the course catalog, which you probably do at least a couple times a year, more certainly simpler, easier, if not a little bit exciting in that you might very well stumble across courses that in the traditional format of a printed catalog or in my.harvard, you might not find these things. So a few of the shortcomings we realized the previous versions. So there were some stupid things, frankly, whereby if you chose some faculty member's name from this dropdown to see what courses this person taught, and then you wanted to undo that process, there was actually no boldface linked up top that said all faculty. You essentially had to reload the page or click clear or go through a non-obvious process. So there was some low-hanging fruit. But the funny thing is, as we'll discuss in a moment, with regard to your PSET 4 gripes with software and machines that you've seen in your life, there's a lot of low-hanging fruit out there in software whereby if you just fix that one stupid bug or shortcoming, you end up making a lot of people happy. So we certainly plucked off the easiest of things. We previously had these links at top left to link to all core courses, all gen ed. And we got comments like, well, that's great, but I'd really like to see what the empirical and mathematical reasoning courses are. I don't want just gen ed in general. And you know, the programmer in me pushed back. And I was like, well, in reading this comment, you could just go over here and type empirical and mathematical reasoning. But the student's comment was fair, because though it may have been obvious to me, the person who implemented that feature, well, if the users aren't similarly identifying how to do something, that's my fault, frankly. And I think if you don't take ownership of this problem and just expect that your users figure it out, like you're not going to end up designing good tools and good products for people to use. So now, for instance, this too, not a hard thing to implement in the end. You click Gen Ed and you actually can select all of the areas or individual areas. So again, some low-hanging fruit. But then there were some more interesting problems to solve. If you used this tool this past fall, there previously toward the left of every course, there were a couple of checkboxes. Check this if you want to shop this course. Check this box if you've taken this course. And there was also a little Facebook icon that if you clicked it would trigger a comments box where you could actually click Facebook's like button and you could start a little Facebook comment thread about the course. And what was fascinating and actually looking at the logs on the server and asking people outright what features they use, like no one even realized you could click this little blue icon, and no one really ended up commenting on courses. So though this was a great idea, we thought, have students have this sort of unofficial channel for commenting on courses, nobody used it. And so we ripped it out, because if it's not being used, why leave it in there as a distraction, even though this idea, we think, still might have some potential. So now we realized it'd actually be nice to generalize the idea of adding a course to some kind of list, because a lot of students didn't want to shop a course this fall, but they wanted to shop it in the spring. And just because we hadn't thought this through fully, we didn't give them away 3 weeks ago to actually shop courses in the spring. So now we've generalized this idea, so you have a little drop down and you can choose courses you're shopping, courses you're taking, courses you've taken. And now it remains to be seen if you all even care about some of these features. But from the computer scientists in us, what we like is the idea of being able to gather this kind of data and understand who's taking what, who's shopped what, but who has shopped something and not taken it. Because if we can build up a corpus of data that really logs the kinds of behavior people exhibit during shopping period, just imagine the kinds of questions you could start answering for people. For instance, I want to take economics 10. Well, what other well, that's perhaps a bad example because almost everyone takes economics 10. I want to take ABC 10. All right, so ABC 10, you might then look at your data and say, well, who else has taken this course? Well, if they've taken this course, what other courses have those people taken? And you can begin to infer with some probability that if you took this course and you're now shopping this course, you might like these other suggestions as well. So for now, we just have some random suggestions at the left. Sometimes it's not so random. CS50 seems to pop up with some recurring frequency for some reason. But this is where we hope to go. And so hopefully now that you're beginning to understand how computers work and how computers think and how you can make them do your bidding, you can start to appreciate the kinds of problems you can solve once you've got some interesting data and really just some basic tools in your toolkit. So if you want to use this tool, by all means, feel free to. The funny thing was, too, we got a lot of comments about features that would be great to add that were actually there. For instance, QGuide data has been in here since the start, but admittedly, it was non-obvious that if you hover over a course, you can actually get all of the data from materials, assignments, workload, difficulty. But our fault if you didn't notice that you could actually get all of that data without having to click through to the course's individual QGuide evaluations. Again, our fault. But the funny thing is, it's very easy for people to make comments on tools and to design things sort of off the top of their head. But it's really only once you sit down and start trying to program this machine that you realize the trade-offs you have to make. There are so many other good suggestions that we received that we decided not to implement, at least not yet, because you also only have a limited amount of space. And if you just keep throwing more and more content, and this too is a recurring theme in problem set 4, you just end up overwhelming your users. So the theme, at least for CS50's applications, which I don't think in general is bad advice, is to try to do few things really well rather than try to do a lot of things poorly. So case in point, another recurring theme that's been on people's minds is, I'd like to be able to tag courses as I might do this for Gen Ed, I might do this for pre-med, I might do this for this. Like a lot of really compelling use cases, but we felt, at least for now, if we tried cramming all the more features into this and we didn't do them really, really well, then it would just be another crappy tool that gets commented on, frankly, next year in problem set 4. So for now, we're going to restrict it to what we think is working well, and then we'll continue to iterate. So again, the takeaway is not look at how we implemented this particular tool, but look at the kind of questions that you yourselves should ask, perhaps, when it comes time to designing your final projects. It's really easy to brainstorm what you think is a brilliant idea on paper in your head, but when you sit down in front of that keyboard and then have to start deciding how to implement this and where to put this feature, it's sometimes non-obvious. So with that said, yeah, we pretty much rattled that off. All right. So with this said, frankly, one of the most useful features that was proposed that is non-trivial for us to implement is this. I want to be able to ask what course across any department can I take in order to satisfy the economics concentration or the government concentration. Obviously, you can shop in the government catalog. You can shop in the economics catalog. But there's a lot of mathematics courses, there are a lot of statistics courses, even CS courses that count for some of those concentrations. And believe it or not, despite how many computers there are on this campus, there is no database that we can find that actually has that information. Rather, you have to read through the student handbook, which is written by humans in prose with bulleted lists and so forth, and figure it out. And so one of the things we thought we'd do, which would be hugely compelling, is to actually make this feature happen so that you can say, I want to major in economics. Show me all of the courses that I could take strategically to satisfy this concentration, even though they might not be inside of economics itself. But there are 5,000 courses in the course catalog. There's like 40 concentrations, all of which are written differently. So we thought we would use a little word du jour these days of crowdsourcing. So if you would like to help us make this feature happen, the teaching fellows and CAs and I have been biting off some of the concentrations. We will share a Google Doc with you. It will be prepped with a certain concentrations columns so that you can then just copy and paste into that spreadsheet which courses can count for primary concentration or secondary field for that particular department. And then within a few days, few weeks, we'll integrate this so that hopefully we will have a super duper app for everyone to benefit then from this spring. So drop me a note if you would like to do that. It's hard for one person to do this. With 500, hopefully if we just get 1% of volunteers, we can do it pretty well. So idea. So when I gave on behalf of CS50 this little intro talk last year at an event called Harvard Thinks Big, the gauntlet I threw down verbally was to have the crowd that was in Sanders that night actually give us ideas, not unlike problem set 4, that they would love to see solved with computers, with a machine, with software, something, frankly, that a CS50 student can do. And if you go to ideas.cs50.net, there weren't terribly many ideas. Right? You can only expect a certain percentage of people to actually follow through on that. But there were some really good ones and also some really fun ones. I thought I'd share some of the highlights. So one suggestion that was made by some random person on the internet after that night was this: a course catalog Android app. Android being an operating system that's increasingly popular on mobile phones. This is absolutely within the grasp of CS50 students, particularly because for every one of the CS50 apps that we've talked about thus far, if you go to follow the link called API, the course provides all APIs, application programming interfaces, which is just a fancy way of saying we have implemented some functions that you can call over the internet from languages like JavaScript and PHP, so that if you want to get data from Harvard courses, if you want to get data on all of the events happening on campus, if you want to get data from the dining hall menu, you don't have to go and copy paste things or figure out how to do that. We will just hand you the data that you want, and you can really dive into the fun part of the problem, solving a workflow, solving a problem that you think you could when handed that data. So something like this. If you already have an Android phone, by all means, can you dive into this? As an aside, industry tends to be nice to the course. Research in Motion, the company that makes BlackBerries, has donated a bunch of phones to the course. So if you would like specifically to tackle a BlackBerry-based final project, we will let you know how to sign up for a lottery to receive one of those phones with which to develop that. So another great idea that came out of ideas.cs50.net. Harvard Travel, a website where Harvard students traveling during J-term or summer can find another Harvard student who have been there or live there, so as to get some info about that place, maybe even be hosted by that person. So very compelling opportunity for one of us this final project season. An application to download all Facebook photos tagged of me. So that's not bad, whatever one's motivation for that. But also tenable. Facebook, too, provides an API with which you can interface with a lot of their data and use it to implement your own idea. Case in point, Harvard courses. You log in with your Facebook account so that you can see, if you opt in, what your friends are taking. And as an aside, if the idea of signing into anything with Facebook kind of troubles you, realize there's a checkbox you can check on our application, at least, that hides your presence from your friends when shopping. You don't have to divulge to the world what you're actually doing. So this was good, too. To reserve a practice room, freshmen still have to go to the FDO and register on a sheet of paper, save some trees, and save some time with a website. So again, some low-hanging fruit there. Now, not all of them were perhaps as technical as that one. This student took the time to write, typo included. This was actually one of my favorite suggestions for how to improve Harvard with a tool or website or piece of software. I don't know, is this a thing now? Because I've never heard this. This one was similarly hardware oriented. We got a lot of things like this. So this is form spam. There's a lot of people with way too much free time and malicious motivations where they don't send you spam trying to buy things. Frankly, they just send you crap like this. And this was submitted automatically via a bot of some sort, a spider, a program that just crawls the web looking for forms to submit. And I actually, a little timidly, visited all of these URLs before class just to make sure I'm not saying go to sketchy.com here. None of them even work. And this was just posted a few days ago. And this fascinating theme of the world of spammers is, one, they rarely speak or use tools with which to write perfect English. So frankly, a really good heuristic for detecting if an email from Bank of America is legit. Bank of America is probably not going to make an email riddled with spelling mistakes. So that's one heuristic. And it's funny, because I'd think if you're trying to capture a lot of people, you'd run it through like Google Translate or whatever the tool might be, or Microsoft Word. And you might actually buy the domain names that you're telling people to actually go to, because these are, in fact, dead ends, at least as of this morning. Other things that, this was interesting. That was one suggestion for how to improve Harvard. Another one, same person. These were from Carlos. Hello, Carlos. And then perhaps related in spirit was this. So perhaps beware that particular application. So frankly, some of the juiciest data that we received, those things aside, were those from problem set 4. So frankly, we could spend all day, all week, all month reading through some really interesting prose. I printed this out this morning. These are 84 pages, two-sided, 12-point font of all the gripes you people have about this place and tools that you've used. But it's really quite fascinating. So what we're going to do on problem set 5 is ask you with a checkbox, are you OK with our posting your comments anonymously to the website? Because there's really some, fun comments in here. There's some really astute observations. And there's really, I think, some food for thought when it comes to identifying these same kinds of problems in your own life. If curious, some of the themes were many people commented on tools close to home like My.Harvard, Hollis, CVS and the Square recently put in this self-checkout system, which at the moment is a disaster, I think. I've never waited longer in lines at CVS than I have the past couple of weeks. And this is, probably a boon for them because they can hire fewer humans, but they put the burden on us. And you see lines perpetually. So that was one theme. Bank of America, people had some gripes with their ATMs and similar. Dining services website, apparently it's hard to find out what's for dinner and what the nutritional content is. And also a theme was sports sites, ESPN and MLB.com. It seems that perhaps there's a theme in that industry of not giving as much thought to some of the user interface issues. There were also some comments, of course, on CS50 stuff, to which we are quite sensitive and will redress. A few things on color blindness issues, where there's some color things we've done incorrectly. So we will take a stab at fixing those. And what else? Oh, there was one comment that it's really hard to find the course websites for previous years, previous semesters instantiations of courses. So in Harvard courses, courses.cs50.net, if you expand a course, you can now see all prior years' websites. We found all the URLs for you. And let's see, anything else do you see here? Oh, OK. So have you ever tried to play a simple game of Halo on the Xbox 360, man's best gaming system? After turning on the machine, you were required to navigate through multiple menu items and obscure system settings simply to get to, quote unquote, play Halo. I would venture that most people who turn on the Xbox with the Halo disc in it are trying to play Halo, not customize their avatar's mustachio. So this, too, is actually a recurring theme. And my soapbox that day with the MBTA is that too often our tools, our problems solved without the common cases in mind. Again, in the case of the MBTA, my God, the common case, I'm going to guess 90%, 80% of the time, is someone wants to use the machine to just get on the next subway to some destination. And yet it's 8 steps. So a clear opportunity for doing something better. Here, you plug in, you turn on your Xbox to play Halo. Apparently, you have to jump through hoops just to play Halo. I have a PS3, which I rarely use, partly because every time I turn the damn thing on, because so many weeks have passed, it wants to do a firmware update and download new software. But it forces you to do that before you can actually play the Blu-ray disc or play the game. Idiotic design decisions, not optimizing for the common case. So if you are amenable, we will invite you to check off a box with which to share these ideas anonymously, because it's certainly a good way at coming up with entrepreneurial ideas, coming up with good project ideas, and really just making you a more astute technical person moving forward. The theme of this course and courses like it, CS1 and BITS in quantitative reasoning or empirical and mathematical reasoning, all of them from the CS department, is really to output students that are not necessarily going to grow up to be computer scientists, not necessarily going to program ever again after this course, but are going to be in positions in society where you're making decisions, and you're making technical decisions, or you're making decisions that affect technical people. And one of the best things we can do in any of these intro sequences, frankly, is at least empower you to make more intelligent decisions than is currently done in all spheres of life, business and politics alike. So hopefully we will have some CS50 alumni in important places someday, so as to make the world a more user-friendly place, to say the least. All right, so a few wrap-up details here. So just to plant this seed, you can, in fact, manipulate data. This is a very awkward transition from changing the world to Bitwise Operations, but so be it. So Bitwise Operations. This is just a mechanism provided by a lot of languages with which you can manipulate data, variables, at a bitwise level. You can change individual bits. You can look at individual bits toward various ends. We looked at some simple examples on Monday at how to change things from uppercase to lowercase. We generalized the idea of using a mask to actually extract data. And one of the themes of problem set 5, forensic, is that kind of thing. Not necessarily using bitwise operators, but really controlling precisely the data that's on disk, the data that's in memory, to extract those details that you want. So just so that you've seen these tools and can tuck them away if ever ever relevant in the short term. Again, the ampersand is for ANDing two bits. It's saying if this bit is 1 and this bit is 1, then the output is also 1. Otherwise, it's 0. Or does something similar to Boolean operators. If it's a 1 or if this is a 1 or this is a 1, or they're both 1s, the answer is again 1. XOR is interesting. XOR actually gives you a lot of neat capabilities in life. XOR says that the answer is 1 if and only if only one of the inputs is the number 1. So if your inputs are 1 and 0, then the XOR of those two values is 1. If your inputs are 0 and 1, then the output is 1. But if the inputs are 1 and 1, or 0 and 0, the output is 0. So exclusive OR kind of does what the name implies. Exclusively, one of the bits must be 1 and not the other. Now, just as a teaser, using this operation like XOR, you can do some neat things. In fact, if you've ever heard of RAID, an acronym, redundant array of independent disks, has to do with the hardware world, but it's increasingly common in desktop computers as well as servers. Using this very simple operation, you can ensure that if you have a computer with 3 hard drives, you can end up using space equal to 2 of them. And the third drive essentially just stores the XOR of all of the bits on the other 2 hard drives. And the implication of this very basic operation is that in such a computer that's using this technology called RAID, you have 3 hard drives. If any one of them dies, the additional one, thanks to XOR, is enough information to recover all of the data. So it's kind of a special trick with which you can have error checking and error detection built into a system. Hugely advantageous. And if interested in that kind of stuff, there are plenty of hardware courses down the pipeline. You can also do one neat thing. For the true geeks in the audience, I thought I'd show you this real fast. Swap2.c. It was in Monday's printouts. This is a copy-paste from our many previous iterations of this notion of swapping. But it turns out I was lying to you when I said you need a temporary variable in order to swap 2 values. Right? The problem always was that if you don't save A or B's value in a temp variable, you're going to clobber one. You're going to overwrite one and lose track of the other. Not so. If you really want to be a geek or you really want to be space conservative, you can actually use the XOR operator, which is implemented in C as a little caret symbol, which is above the number 6. This is the XOR operator. You can execute these 3 lines of code here down at the bottom. And it turns out, nearly magically, these 3 lines together will simultaneously, conceptually, move the bits from A to B and B to A without losing any of them. So it's kind of a neat operation, but not something we'll dwell on today. So things that we can do, though, include or other details that are relevant are this. One of the themes, too, that comes up in problem set 5, forensics, is in actually reading in bytes from disk and actually comparing them, looking, for instance, for the special signature that JPEGs have. If you haven't read the spec yet, a JPEG image almost always starts with the same pattern of 4 bytes. And that pattern means here comes a JPEG. And if you see another such pattern, that usually means here comes another JPEG. And leveraging that very simple hint, those 4 bytes alone, can you essentially, with high probability, recover lots of JPEGs. And that's one of the goals of that P set. Well, it turns out that depending on the operating system or the computer architecture, the CPU that you're using, sometimes numbers, if they are multi-bytes, as integers are, as doubles are, as longs are, depending on the architecture, sometimes those bytes are laid out in opposite order. So just, again, to plant the seed so that you've seen it, and if you run into certain bugs that the teaching fellows address in section or office hours, it makes a little more sense. Realize that there's 2 ways of implementing numbers on disk. You can either take all 4 bytes and essentially write them to disk left to right, or you can write them to disk from right to left. And the effect here, this is a little screenshot from Wikipedia, a decent article that discusses this issue. Essentially, if you're using a big endian architecture, the number is laid out just as we've been thinking about it. But little endian architectures, which is very much in vogue these days, Intel CPUs use this thing called little endian. If you actually look at the bytes at a low level, what you think should be over here is actually over here. And again, we won't spend time on this today, but just in case you run across certain bugs in problem set 5, and we point you toward this notion, just realize there is this subtlety that differs among architectures where numbers are stored differently. But you will be playing with pointers a bit on this problem set. And so one of the other files from Monday was this thing here, pointers1.c. This program is actually pretty old school at this point. This is just a program whose purpose in life is to get a string from the user using our getString function. We store the return address in a variable called s. Why do we check for null here? What might actually go wrong here? So it may not be a string. And in what situations might getString return null, like someone from over here, perhaps? So not enough memory, right? If the user's being annoying or malicious, or the computer is just very memory constrained, if the user types in something too long to fit in memory, then malloc is going to return null. And recall that getString uses malloc, and so this too will return null. If you don't check for null and just proceed along your way and dereference a potentially null pointer, what of course happens? Segfault with high probability. Not always, but with high probability. So this part of the code here just does some old school stuff now. We loop from I equals 0 on up to n. What is n? Well, we initialize n to the return value of string length. So this loop is going to iterate conceptually over every character in the string s. And then it's just going to print it using s bracket I notation, each char one at a time, one character per line. So again, I say old school because there's nothing new here today. In fact, it's a bit of a regression using strings as though they were arrays, which is very convenient notation. But we've, of course, been talking about strings as pointers lately, so much so that we now have been preaching this habit of freeing any memory that you allocate with malloc, or in turn, any memory that you implicitly allocate using getString, because it again uses malloc. And so one of the themes for problem set 6 will be to use that tool, Valgrind, from Monday to actually help you find situations where you're forgetting things like free. But the fact that a string is really just a memory address, it turns out that you can do the same kind of program, but treating s as though it truly is a pointer. And so you can use something called pointer arithmetic. So again, just to plant a seed here that will recur perhaps in problem set 6 or in future courses if you continue on, this program, again, just gets a string from the user, stores the return address in s, and does this little null sanity check. This for loop is identical up here. The only thing different about this program at the moment is that I'm using this, star parenthesis, s plus I, close parenthesis. So star, remember, is the dereference operator. It means go there. So how is this actually doing the same thing? Well, just so it's clear what both of these things are doing, let me run pointers. Whoops. Oh, interesting. Bug. All right, standard lib. I screwed up. So let me recompile. It was complaining that it couldn't find free. So let me run pointers2, enter, hello. That's all this program and the predecessor version did. It just prints the word, one character per line. But how does this version work? Well, if s is an address and it's pointing to conceptually a string, what it really is the address of a character. And the string is just the result of going step by step by step by step until you see what special character, demarking the end of the string. So the null terminator, which is not null, but \0, right? That's the special character we look for. So what this is really doing is it's saying what? Take s, which is an address. It's like 0x12345, some location in RAM. It's adding I to it. Now, initially, I is 0. So initially, this is meaningless. It's just s. So star s means go there. Well, when you go to s, what's waiting for you? Just a character, right? If it's the address of a character and you go there, obviously what's waiting is a character. And so we can continue using %c, and we print out that character. Well, now iterate one more time in the loop. So now I equals 1. So s plus I is whatever the address is, 1, 2, 3. Now we add 1. Now it's 1, 2, 4. And so now we say go to address 1, 2, 4. Well, what's waiting for you there? The next character, because arrays are contiguous. So what's neat at this point in the course, now that we've peeled back this layer of the CS50 library and this layer of array notation for everything, in fact, when you have a pointer, you can go anywhere in memory that you want. And the fact that you can just come up with an arbitrary value, perhaps arithmetically like this with some addition, means that you have great power, but again, also great risk in your programs, as we've discussed in the context of buffer overrun exploits, because if you can do it, so might someone who actually has malicious intent and somehow tricks you into running code that you yourself did not write. So that is generally known as pointer arithmetic, but it's really just how that square bracket notation has been working all of this time. So any questions about bitwise operators or pointers?
When you said s plus I, isn't that adding a pointer to an integer?
Isn't it adding a pointer to an integer? Yes, but that's OK, because in this case, the integer will be essentially implicitly cast up to an address, and it will work OK. This notion of pointer arithmetic is built into the language. So it is permissible, even though it is, in fact, two different types, a long and a pointer. But it's legit. All right, so now the proverbial fun begins that I keep promising, if only because now we get to really think about and talk about some ideas that you can start taking for granted, frankly. Once we get to web-based programming, you'll find that in languages like C, and, languages like PHP and JavaScript and Python and Ruby and Java, and there's so many other languages out there. And rest assured, frankly, generally, you just need a good foundation in one language, maybe 2, 3 languages, and the rest you can teach yourself. I mean, case in point, in school I took CS50, where we learned C, CS51, where we learned a language called Lisp and C++, and that was it. I never again formally learned any languages. I bootstrapped myself from that process, and this isn't because I was particularly cut out for CS, but it just really is true that the marginal returns on some foundations in different types of languages is pretty huge. So one of the themes next week onward is that we're going to move pretty darn quickly through PHP and JavaScript. We're not going to teach you the whole language, because frankly, you're going to see that for loops look almost the same. While loops look almost the same. There's going to be some more functions in PHP, which is great, because it means you can implement fewer uninteresting things yourself. But what you'll find is that one of the goals of the next few weeks is to help you realize, by doing it together, that teaching yourself new languages is absolutely quite possible and quite useful when you're in some lab or some job, even frankly in the financial and consulting industries, where a lot of my friends, case in point, never once programmed in school but are now doing it as part of their analytics work. So you learn, and better to learn in advance than have to learn on that kind of job. So we talked about stacks as a new tool with which to implement a data structure. And a data structure is generally just a convenient mechanism for representing data so that you can solve more interesting problems or solve problems more efficiently. So arrays were fairly limited. Linked lists gave us some dynamism. But the problem with linked lists really is that it's just this long line of people, long line of numbers. We lost the division and conquer capabilities. We lost the binary search capabilities that we started the course with. So can we get some of those features back and yet more of them? Well, just to tidy up a loose end, I felt bad in that I completely I felt I did not express very clearly how one might go about implementing a stack or a queue. And we won't spend great time on it because you can spend entire weeks discussing the implementation details. But I at least thought I'd propose a canonical example to kind of clean up my verbal mess for Monday. So here is how you might implement a stack using some basic building blocks. So again, a stack is akin to the stack of trays in dormitory. So typedef struct says, here comes a struct. The last word there says stack, which means I'm going to give this structure the name stack. So really, the interesting part is inside of the curly braces. Now, a queue, or rather a stack, presumably has some fixed length. That's generally the assumption in the world of stacks, that, yeah, you could stack cafeteria trays ad nauseum, but at some point it's going to fall over. So realistically, there is some upper bound. And certainly in a computer, there's going to be an upper bound based on the amount of memory that you have. So it stands to reason that this data structure generally has a fixed size, which means we can actually implement it using an array. If we know it's going to be a fixed size, we can just allocate that memory at the beginning. Let's assume that capacity, in all capitals here, is just a constant declared somewhere else that's 100 or 200 or whatever. It's a fixed value. So this says the structure called stack is going to have an array inside of it, in this case called numbers. So this appears to be a stack that stores just numbers. So pretty simple application, just store some numbers. But I need to remember some key details. Initially, I might have space for 100 integers. But there's not necessarily 100 integers in there. I probably have 100 garbage values. Or if I take some care, I might have 100 zeros or negative ones if I initialize the whole thing to some known values. But the point is that it's not sufficient to just say, here's a chunk of memory, now you have a stack. You now need to have some metadata associated with the structure to remember what's in there and how much of it's in there, so that you don't risk returning some garbage value or overstepping the bounds of your array. So I'm going to remember, one, the size. So size is distinct from capacity. Capacity means how much space is there, and size means how much space are you actually using. So initially, I'd probably initialize size to 0, because there's nothing in an empty array by default. And then top. So I chose top specifically because if I'm stacking cafeteria trays, really the only number I care about is where in this array is the topmost tray. Where in this array is the topmost number? Now, why would the topmost number not just always be at bracket 0? Right? If I have an array, it feels like the logical thing to do is to put the top of the stack in bracket 0. Now, why is a stack's implementation not as simple as that? Why do I need to remember separately where the top of it is? Yeah?
Like if you're adding them, you don't want to reshift them all just when you put a higher number.
Yeah, exactly. So it's a design decision. I could absolutely start by putting numbers into this stack by just starting at bracket 0, then bracket 1, then bracket 2, right? Old school style, totally reasonable. But if the point is to maintain some kind of order, I need to remember which one went in last so that I take it out first. So it's a LIFO structure, last in, first out. So in that case, if I start at bracket 0, putting in some number, I put a tray down. Then I do it again at bracket 1. That's another tray. Then another number. That's a third tray. Really, the number I care about at this point is not bracket 0, because that's actually the bottommost tray that I don't really care about until I get there. I need to remember bracket 2 at this point. And so using this variable, this metadata, like top, can allow me to remember that the current top of this tray, or this stack, is just the number 2. And size, by contrast, is 3 in this case, because I've put 3 elements onto the data structure. Yeah? Good question. Would size always be top plus 1? Could be, but what if we start putting in like 100 numbers, then we start popping off numbers. Pop is the lexicon for removing things from a stack, much like a cafeteria stack. So if I do this, I start putting in number, 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 and now I hit the end of the queue, and I've started popping element. So I've kept going up and up and up and up. I've started putting numbers into the queue. Actually, is this? Let me debug this in my head for a moment. Yeah, this was kind of stupid. All right, so this is not, in fact, necessary. I was conflating it with a queue. So I will fix this verbally in a moment. All right, almost had it correct this time. So let me come back to that in just a moment and transition to this with the wave of the hand. But then we'll fix that one in just a moment. So the other notion was a queue. So a queue is the real world concept of actually having like a line of people. And you want to maintain fairness. So it's a FIFO data structure. First in, first out. The first person into the structure is the one you want to remove from the structure first. And so we might implement this as follows, whereby we have an array called numbers again with the same kind of capacity. Here we have size, but here we might want to remember where the head of the list is. This is what I was thinking here. So in the context of a queue, you might very reasonably in your code put the first person at bracket 0, then the next person at bracket 1, then the next person at bracket 2. So at that point in the story, size is 3, but head, the front of the list, is 0, where the first person was. Now, if you remove the first person from the queue, you now conceptually have this hole in your array, whereby you still have a space at bracket 0, but there's no human actually waiting in line there. So what could you do? You could just move all these humans or move all these integers over by sliding them in the array. But what's the running time of shifting an array over one space to the right or to the left? It's linear, right? In the worst case, you've got an almost full queue. You've got to move every darn number over to the right or to the left. And what's the point, right? Instead, I can just remember where the head of the queue is. And so the size might be decreasing, but the head is moving. And then in this case, with a queue, I might, to save time and memory, I might want to wrap around at the end and reuse all space, in which case I might very well want to remember where the tail of the queue is, so that I essentially treat my array conceptually as a circular structure. I don't care where the start and the end is in memory. I just have to keep track of it with these variables. So I'll go back before long, and I'll clean up the stacks structure. But let's focus now on ones we'll deploy in problem set 6. So problem set 6, recall it will hand you a huge text file with 140 some odd thousand words from an actual dictionary that you might use in Microsoft Word or really any tool that can spell check. Unfortunately, it's just a text file. It's got 1 word per line. But all it is a text file. And so one of the things you're going to have to use is your newfound comfort, or by Friday, newfound comfort with file I/O, to read those words in from disk and then to load them into memory. Now, the simplest implementation of a spell checker might just be, all right, allocate an array that's 140,000 in size, so that you have 1 location for each string, and then you load each of the strings into those locations. The upside of this, because the file we'll give you is in fact alphabetized, which might be useful, the upside of this is that now you can use like binary search. If just conceptually you've got a huge array and you don't have numbers and you don't have humans in each of the slots, you have actual words, well, there's that function called stir-compare. You can absolutely use binary search on a really big array to find some words, so that when your program asks the question, is the word the user just typed in spelled correctly, you just go boom, 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 using binary search on your array, and you can return true or false. Now, is that the best approach? It's not bad. What's the running time of binary search on an array? Right, so log n. And log n, frankly, has kicked the butt of every other algorithm we've looked at just yet. But as promised on Monday, the holy grail really would be constant time. Like, I don't even want to wait for log n time, which for large data sets, it might be asymptotically fast, might be theoretically fast. But if you have large enough data sets, not just 140,000 words, but a billion web pages or 500 million users on Facebook, even binary search on a data set that size might very well take some time. So certainly, returning it in constant time, one step, conceptually, would be optimal. And so enter into this picture the notion of a hash table. A hash table is often implemented as an array, but it's implemented as an array that's bigger than it needs to be to store all of the words or the numbers or the whatevers that you want to store in it. And the idea is essentially, if this is my hash table, this is just a big array. And on the left-hand side, I've just numbered the locations in the traditional way, 0 at the top, 1, 2, 3, dot, 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 down to 25 in this case. You can think of a hash table conceptually as being a data structure where you take some input, whether it's a number or a string, and then you kind of like darts, throw it into the data structure and hope that it actually sticks and doesn't hit some existing value. Now, that would be more dramatic if it actually stuck. But that was off the top of my head. We'll come with sticky things next year. If you throw this input, this number or this string, into the data structure, you're going to hope that it lands in some blank spot, as the board currently is. And that's great, because how much effort did it take to put my string or my int into pretty much a random location? That was one step. It took me one throw to actually hit the data structure. But there's a downside. What's an obvious downside? So if there's something there, right? So this idea of probabilistic insertion into a data structure could get you into trouble. If you've got a huge data structure and only 3 pens to throw into it, you know, statistically, you're not going to have any collisions. And so odds are you'll have too much space, but at least you won't collide, which means all of your data will fit in there. And so that's pretty good. But if now you have lots of data in there, the odds of throwing a new item into your data structure and having it stick in some empty location is pretty actually low. And plus, even when you go through this process of throwing something into the data structure, well, how do you then find it? Right? Insertion is pretty damn easy. But what about search? I mean, who knows where it ended up? So we clearly can't just randomly pick the insertion point. Otherwise, we're killing the running time of the search algorithm. And arguably, what I care about most is finding this data in the future. Right? I'm putting it into a data structure, presumably, in order to create a situation where I can get it back in constant time. So randomness certainly isn't the case. But let's suppose that it is random. And let's ask ourselves, if you have a container, a table, a hash table that's initially empty, and you just throw randomly some pens into it, you know, what really is the probability of having a collision? Well, it turns out, even though I said verbally, the odds of my hitting another number, it's pretty small, it's actually not. And if you've ever heard of a little mathematical problem called the birthday paradox, you can model this question very easily and see that, even if you have a whole lot of memory and relatively few things to throw in it, you're still very likely to actually hit something that's already there. So we can frame it as this. In a room full of n CS50 students, where n is declining over the weeks, what's the probability that at least 2 students have the same birthday? So this is kind of the same problem. It's just framed in kind of a silly way. But here, the hash table is 365, or maybe 366 for leap years and such. But we have a hash table of size 365. If we assume that your parents had children by a uniform distribution over the year, which I don't think is actually statistically true, we can assume that if we throw all of your birthdays into this bucket that's of size 365, that we'll get collisions eventually, but at what point? Now, with a class of 501 students, you're going to throw those birthdays into a data structure size 365, and obviously you're going to have collisions, because you can't fit that many people into that few buckets. But even if you're taking a smaller seminar course that's only 40 people, turns out it's very high probability that even in smaller classes, you're going to have collisions. And this is an experiment you can run, frankly, in your next section or your next seminar class. And we can model it as follows. If you ask yourself, when I throw the first birthday into this data structure, what's the probability of a collision? Or what's the probability of it not colliding with anyone? Well, it's 100%. The data structure is initially empty. You have a 100% probability of not colliding with anyone else. So this actually turns out to be one of those problems where it's a little easier to answer the opposite question, not what's the probability of a collision, what's the probability of no collisions? So that's the question we're asking. Well, for that first person, it's 1 divided by 1. There is a 100% 100% certainty that I'm not going to collide if it's the first birthday. What about the second person? Well, it's a pretty easy problem. It just means that person obviously has a birthday. So it means there's 364 other buckets that they can fall into without a collision. And so we can model that as 1 minus 1 over 365, which is just 365 minus 1 over 365. It's 364 over 365. Now we do this again and again and again and again, and we ultimately get a formula that we could plot, and we can actually see at what point the probability becomes worrisomely high. And so in the end, if you work this out, not to scare with the exponents and such, this is the concise way of expressing the probability we're discussing verbally there. But it looks like this, and this is the neat takeaway. So if you have just one person in the room, one birthday, there's a 0% chance of a collision, of a match of two birthdays. But notice this curve. This is 100% chance, 90%, 80% chance. I mean, notice how quickly this formula hits 90%. And that I picked off 40 specifically because of this reason. It turns out statistically, if you assume a uniform distribution of reproduction, then you will have in a class of 40 people with 90% probability a collision of birthdays. And once you have a class of like 58 people on the right, it's a near statistical certainty. So this is kind of a neat sociological curiosity. But for us, the question is actually very germane, because if we're trying to create a data structure that has some fixed size, because we only have so much memory in the world, we want to over allocate memory, because we need to have some holes in this structure with which to avoid collisions with higher probability. But it looks like we need a super amount of memory, way more than 365 buckets, just to fit a 40-person seminar class. So the assumption we've been making, though, thus far is that it's this uniform distribution of numbers. What if we actually look at the input, the birthday, or the number, or the string that we're inputting, and try to figure out its location, not randomly, but actually analytically, so that we minimize the probability of collision? And so that's what we'll do after a 5-minute break. All right, so we are back. So one amendment. So I finally remembered why in the implementation of a stack here in a C data structure that I had both size and top. It was actually for one corner case. If you only have top to remember where the top of the stack is, there's one gotcha, which is when the stack is initially empty. And so if the stack is initially empty and you initialize top, for instance, to 0, you might otherwise return a garbage value. Now, there's a way to fix this, of course. You could just declare top to be some sentinel value, a special value like -1 to signify that there's actually not something here. Or you can take this alternative approach and just maintain it as a separate int, which was the approach I took here. But actually, a decent takeaway here, or save for me, is to say that though we might introduce these structures in one way, there's absolutely different decisions you can make. And in fact, one of the themes of pset6 when you implement your spell checker is going to be to decide for yourself what would be the best way to implement this structure or that. And you'll be guided toward a couple possibilities in this Sunday's walkthrough for pset6 in particular. So the question at hand a moment ago was, what's the probability of a collision? And the takeaway is really, it's pretty damn high. So the collisions are going to happen. So we need to be able to mitigate these somehow, or at least deal with them. So what's the simplest possible implementation of a hash table? Well, the simplest one, arguably, is just an array of fixed size. And you take your input, let's say an integer, and you try to put it into the hash table at a specific location. And if there is a collision, as we say, if there's something else already there, you know what? The simplest fix is just move it then to the next bucket. And if there's something there, move it to the next bucket. You know, just make a best effort to find an empty location. And if you hit miss, then just increment plus, 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 plus until you find a hole in the data structure. Now, what might this mean? So when you throw a pen at the board, you're doing something that's generally called hashing. To hash as a verb generally means to take as input a number or a string or something, and then return as output the intended location for that input in the data structure. So we might implement a very simple hash function as follows. If I need to return an int, because again, the role of a hash function, let's call it hash, is to take as input, let's say a number, and then return as output the location of that number in the hash table. It's answering the question, where do I put this? And now we could, as I did physically with my pen, we could just do something like return rand. Right? So that would be the simplest approach. And that's actually not quite right. I'd actually have to multiply it out so I get the range correctly. But we could use rand and actually get back a random value. But again, to be clear, what's the downside of putting an element in any data structure at some random location? Which is pretty fast, but there's a downside. search, right? You can't find it again unless potentially you search through the whole data structure. And the worst case running time there is probably going to be big O of n. Because if it's in some random location, it might be in the last location you check just by bad luck. And so that's not the best goal here, right? We could have done better, frankly, with binary search and arrays. So that's a step backwards. But we could do this. Suppose that the input is n. And let's suppose that we've got a pretty big data structure. You know what I can do? If I want to store the number n in an array, where should I put it? Well, the common sense in me says, why don't I just return the number itself? So if I'm trying to insert into this data structure the number 0, where should I put it? How about bracket 0? And if I'm trying to insert number 1, where should I put it? How about bracket 1? How about the number 25? How about bracket 25? How about the number 26? Oh, there's the problem, right? If your inputs might actually exceed the bounds of your data structure, which isn't a deal breaker, right? Because if they're sparse, if you have a number over here and a number over here and over here, you don't need a super big data structure in order to store it, like some of you for the hacker edition of pset 2 might have to get linear sorting time. Well, we need to actually exercise a bit of intelligence. So what's the best way to avoid wrapping around to the end of a data structure that's only of size, let's say, 26? How do I change this formula? All right, so modulo, right? So modulo is kind of our savior when it comes to wrapping around. So this is better. Now, if my goal is to insert an integer into some data structure, and that data structure is of size 26, well, now, thanks to modulo 26, no matter how big my input is, whether it's 0 or 25 or 26 or 2,000, I'm always going to get back a number between 0 and 25 because of modulo. And so that will definitely fit. But if you're allowed to have these super large numbers going into a fairly small space, what's going to happen when you hash into, as input, the number 0? Well, it's going to go with bracket 0. What if you hash in the number 26? Where is it going to go? Bracket 0, right? Because 26 mod 26 gives you no remainder, which means bracket 0. So again, you get collisions. So one of the solutions to this might very well be conceptually. We won't do this part in code because it's easier to just do verbally. Well, one of the solutions might be if I try to hash into location 0 and something's there, we'll take the location I tried to hash into, just do ++, and then check location, in that case, 1. If it's an opening, put it there. Now, how do you find that element in the future? Well, it's the same process. If I am asked the question, search for the number n, well, I first run it through the same hash function, and I get back the same answer, 0. So this function, search, is going to go ahead and check at bracket 0 for the number n. Is it there? If so, returns true, and search has done its job. If it's not there, should I immediately return false? So, right, probably not. I don't want to return false because where might it be? At bracket 1 or bracket 2, or worst case, and here's the gotcha, worst case, what if the whole array was so damn full except for slot number bracket 25? Even my number 0 or my number 26 could, by bad luck, end up all the way at the bottom of the hash table. So this method that we're describing is generally called linear probing, whereby you probe at subsequent locations in the hash table, just looking for an open space, looking. But it's linear in that you keep doing like a ++ operator. And the downside of this, of course, is that if you've got a lot of inputs or a lot of bad luck, and you keep hashing to the same locations, and they're all kind of blocking together, so you keep having a ++++++, this algorithm ultimately degrades into big O of what again? So n. So it's a little better, perhaps, than an even more naive approach, but it's not perfect. So we need something better. Yeah? There may be a number there. So this is incomplete. So what I really need to do here is, in pseudocode, if something at location, actually, we'll just use pseudocode. If something at location this, then I need to, not to induce giggles, but probe array. Right? So keep probing down further into the array, looking for, and that would be implemented with a while construct or a for loop or something like that. So just some pseudocode for now. Now, this is not a very interesting hash function, right? This is just for integers. Let's still return an int, because hash tables ultimately boil down to the question, where should I put this? But let's do something more interesting, like a string. So if I want to take in a string s, I can't just return, for instance, return s ampersand n. I kind of could if I dealt with the casting, but s is a pointer. It's pretty meaningless to take the pointer and just hash it in this way, although you could do this if you really wanted to. But this doesn't feel very intelligent. Suppose that the strings I'm trying to insert into this data structure are people's names, right? And so that's actually why this hash table by default has only 26 locations, because I'm assuming that there's a 26-letter alphabet, A through Z, and ignore uppercase and lowercase for now. Let's just suppose that I really want to put in names into this hash table ideally without having collisions. So what might be the best approach if my input is someone's name like Alice? I'm given a string, ALICE \0. How do I convert Alice to a number that tells me where to put her name into this hash table? Oh, what was done here? So we could add the ASCII values. We can actually do a little simpler. I'll push back first. So we know that a string is just a bunch of characters. So we know, and characters are just numbers. So if the goal is to get a number, we can kind of leverage the fact that characters are represented as numbers. And in fact, let's not add them all together just yet. Let's go super trivial here for now. Let me go ahead and return s bracket 0 cast to a not char, cast to an int, right? Let me just look. It's a little heuristic, might get me into trouble, but I could return the integral value of s bracket 0, but there is a bug here. What's this really going to return to me? This is going to return like 65 if it's capital A, or 66, and already these numbers are beyond my boundaries. So really, I should be doing something like this. Return s bracket capital A. And I need to whip out some code from like Caesar or Visionaire where I actually converted these things to numbers between 0 and 25. So I could do something like this. And I don't explicitly need the cast. It will happen for me. But this would take the character at the first letter in the word, subtract off capital A, and let's assume for simplicity right now it's all capital letters. And this is going to give me a number between 0 and 25. Again, I need to improve this. I need to write better code to handle lowercase numbers, maybe weird punctuation or strings that start with numbers. But in the simplest case, if I'm getting an all capital word, this hash function would work. But would it result in collisions? And if so, under what circumstances? Yeah, so obviously you're going to have a collision if the two names start with the same letter. So Albert and Alice are both going to try to hash to location 0, so we have a collision. And I'd wager that that's going to be pretty common, right? If you've ever played Wheel of Fortune, there's certainly some letters in the English alphabet that recur more frequently. And odds are, if we look at the class list, I'm guessing we don't have that many students whose first names start with Q. Probably not Z either, right? There's some relatively infrequent characters. If that is, in fact, your name, great. We have a spot for you in the hash table. But there's going to be a lot of people with B's and D's and C's and all of that that are just going to collide. So that kind of suggests that though this is nice and simple, it's constant time, right? There's no loop here. There's no algorithm. There's no looping process, which is why I pushed back on the idea of adding all the ASCII values, because that would take more time. Let me pluck off the first one. But it's flawed in that I'm going to have a lot of collisions for the A's and the B's and the C's. And I'm like always, with high probability, going to have an opening for this person where Q might be, or where Z might be, or where X might be. And this feels like I'm wasting space. So an opportunity for problem set 6, when you're given words from a dictionary, is going to be to answer this question. Do you want to go naively, but simply looking at the first letter? Or do you want to do something a little more sophisticated to minimize that probability and use something that takes more input into account? So what's the solution really to this problem of collisions, right? Even with linear probing, you're going to end up filling all of the spots eventually, and then you're out of luck, right? Then the data structure needs to be entirely reallocated, which is hugely expensive, right? Making the decision of size in the beginning is probably better. So a better approach is something like this. So this picture here isn't about names, but this one here is about birthdays. This is an array on the left-hand side that is numbered from 1 to 31 to imply that we're assuming that every month has maximally 31 days. And the goal here is to take some people as input and put them into the hash table's location that corresponds to their birthday. So if you're born on the 1st of the month, you'd go at location 1. If you're born on the 29th of the month, you'd go at location 29, irrespective of the specific month and year. So this is called separate chaining. And this pretty much is an obvious solution to the problem of collisions. You know what? If you have a collision, don't try probing the rest of the array just hoping you're going to find an empty spot. Because again, the downside of that is linear running time for search later on. You know what? Stay where you are and just tack on the additional word or the additional input onto a list. That might grow over time, but at least stay where you are. So here's what a hash table really generally looks like. These are something we'll take for granted in PHP and JavaScript in the weeks weeks to come. But a hash table underneath the hood is very often implemented as something like this. It's still a fixed size data structure where you have maybe 26 or 31 or a billion locations into which you put even more data than that, right? Linear probing was flawed in that you could only fit 26 elements. Separate chaining frees you from that arbitrary limitation by allowing you to have essentially this really clever amalgam of the thing we called an array and the thing we called, on the right-hand side here, linked lists. It's kind of a merger of these two ideas. And so with separate chaining, we still get not theoretically better running time, but we get much better distribution of our values. If we've got n elements, just to put some formulas on this, if we've got n number or n people that we're trying to put into this data structure, and suppose that the distribution of birthdays is uniform over 31 days, well, how long is each of these chains going to be? If we've got n people and we've got chains of length and we've got 31 possible chains, well, if it's a uniform distribution, you divide n total inputs by the total number of buckets you have. So this implies that after you start inserting a whole bunch of people into a data structure like this, even though this picture is a little ragged in that there's some short chains, there's some long chains, there's some no chains, in the end, if you assume a uniform distribution, you're going to have chains that are all roughly the same length. So that kind of means that the running time for search in the end is going to be something like big O of n over 31. But let's generalize this, n over k, where k is the number of buckets that you have. Now, the mathematicians might realize, well, k, if it's just a constant, every time we talk about asymptotic notation, we cross out things like constants. So the little white lie here is that a hash table's running time is still big O of n. And so fundamentally, theoretically, it's no better than linear probing. It's no better than an array. It's no better than a linked list. But now, as we get to problem set 6 in the web-based aspect of the course, where we start solving some more real-world representative problems, in the real world, taking a big number n and dividing it by a decent-sized number k, that's actually 1/8 the running time that it would be if it were n. So in the real world, though we might cross out these constants in asymptotic life, in the real world, constant factor differences actually make a difference in terms of the human time and the amount of cycles you're actually spending. So one of the goals of pset 6 will be to kind of say, yeah, I know asymptotically this is still a linear time algorithm, but look how damn fast my code is because I have a lot of buckets and I have fairly short chains, and I've made some design decisions underneath the hood that really expedite in the real world the solution of this problem, namely spell checking. How might we implement this? Well, we might implement this with some nodes here. So again, I made the mistake 2 weeks ago of not defining what a node is. A node in computer science terms is just some kind of container. It's some data structure that generically is called a node, and inside of it is some stuff that's interesting. So each of these little rectangles here, we're going to call a node. We talked about nodes in the context of linked lists. It looks like, based on this picture, each node has a string, a person's name, and then this little square, which is meant to represent a pointer. So the translation of this might be a node struct in C like this. Every node in this data structure has a string, a word, someone's name. And let's suppose that length is a constant defined elsewhere. No one's name is going to be longer than like 50 characters or 1,000 characters. There's some upper bound into which everyone's name in the world fits, even if it's large and variant. Well, this just means maximally everyone's name can be length plus 1 characters long, the plus 1 being for the null character. Now, I also need inside this node another pointer to another such node, and that's why we have sort of this circular reference to something called a struct node. But this is very, very similar to what we did for linked lists. It's just with linked lists, we didn't have a character word array. I think we just had an int the day that we looked at linked lists. So this might be one approach for implementing that kind of structure there. Well, what more can we do? Now that we're starting to take arrays in this building block and linked lists, and we're wiring things together with pointers ever so cleverly, we can really start implementing arbitrary shapes and sizes inside memory toward an end of solving problems with data structures that are most conducive to the problem at hand. So in computer science, there's this notion of a tree. It's kind of like what we'd think of as a family tree, where you have the oldest member of the family at the top, the so-called root of the tree, and their children, maybe a left child and a right child, hang off of them pictorially with arrows, suggesting that each of these circles is a node, another type of node. We drew it as a circle. But each of these pointers just points to another member of the family and another member of the family. And the idea of it being drawn from top down means this is like grandpa. This is mom and her brother or sister. This are her children, grandpa's grandchildren, and actually this the grandchild here, and so forth. But it doesn't have to be viewed as a family tree. Really, the lexicon we care about today is this is the root of any such structure, the thing that's at the top that holds it all together. You call any descendants of a node the children, just like you would a family tree. And then any nodes that are at the very bottom that have no children of their own are generally called in graph theory. This is an example of a computer science graph. They're called leaves. So that's just some jargon. Let's actually do something interesting with it. Well, we had an array back in the day for representing numbers that we were able to use binary search on. It turns out, even though this is not a fundamental improvement over an array, because now we have some overhead of pointers, it turns out now that you have the ability to wire things together dynamically and kind of branch out in different directions, you can resolve some of those same problems. And we'll see more interesting problems using more interesting data structures. This, in fact, is kind of equivalent to a list in that we have an array of numbers in that we have 22, 23, 44, 55, 66, 77, 88. And it's intentional that this picture is drawn in the way that it is. Notice that every number to the left of some node is smaller than that parent, and every node to the right of some node is bigger than that parent. So here's 55. Notice how 33 is obviously smaller, but so is 22 and 44 because all descendants of a node are, by definition in this structure, smaller. And same deal over here. 66, 77, and 88 are all bigger than 55. Well, now what's really neat is that you can find things in this structure using not only binary search, but finally that technique we called recursion. Right? Recursion was the act of a function calling itself, or more generally, it's the act of doing something and then doing that same something again, but on a slightly smaller problem. Well, how does that apply here? Suppose I am searching for the number 44. This data structure is generally called a binary search tree, the search meaning that the numbers are laid out in this special order, smaller than on the left, bigger than on the right. So I'm handed the root. So just like a linked list where I'm only given the first node, same deal here. When you're given a tree in memory, all you need is one pointer to the root, and then everything else hangs off of it. Well, notice here what I might do is search for 44. I say search 44. I'm handed the root. Well, is 44 equal to 55? No, obviously not. Is it greater than? No. Is it less than? Yes. And so now I can chop this problem in half, just like the phone book from week 0, leaving me with a problem that's half as big, but it's the exact same kind of problem. So suppose that the search function that I'm describing here verbally takes as input an int, and it takes as input a pointer to a node of a tree. Well, you know what this thing on the left-hand side here looks like? It kind of looks like another tree. So another piece of jargon people tend to use is, yes, 33 is the child of this node 55. But you know what? 33 is also the root of his own tree, a smaller tree, but that has its own children. So if I'm implementing code now called search, and again, it's a function that takes an int as a parameter and a pointer to a node as a parameter, well, I can just call that same search function again on the left child pointer. And the only time I want my recursion to stop is if I find the number in question or there's no children. Right? I obviously don't want to keep calling the same search function on a child if it's not there. So this begs the question, how do you implement a node like this? Well, we can translate this pretty identically to the picture at hand. So I'm going to define this thing now as a node. So again, I'm redefining node all the time. And that's what I mean. A node is just a generic concept to describe some bucket of information in a picture. So in this case of a binary search tree, well, we need a node to have a number in it. We also need that node to have a left pointer and also a right pointer. Now, we could call these foo and bar. We could call them anything we want. But conceptually, they're meant to point to two other nodes in the tree. Now, you can get yourself into trouble, right? You can start wiring this data structure together with loops and crazy sort of redirections, and you can get into cycles where then your code might very well get into an infinite loop. Well, what's the solution? Well, don't do that. If you start implementing cycles, you're then implementing really what people call a graph and not a tree. When you're implementing a data structure like this, it's up to you. The burden is on the programmer to actually get the details right. Well, now if we are moving toward a tree, let me propose another approach to a spell checker or a dictionary. Thus far, we've emphasized hash table. And again, a hash table is pretty decent algorithm, pretty decent data structure for a dictionary. To be clear, even though we talked about birthdays here, you can imagine taking as input a string, a word in a dictionary, and somehow using its ASCII values or something like that to come up with a location from 1 or from 0 on up to whatever the size of the hash table is, and then put that string there. Well, that could give us pretty good running time. Big O of n over k is technically big O of n. But as you'll see in the real world, hash tables tend to be pretty darn fast. But there's also this thing called a trie, T-R-I-E. It's meant to imply retrieval. A trie is an interesting data structure that we'll also talk about, incidentally, in this week's walkthrough, that is essentially a tree, each of whose nodes is itself an array. So this is kind of trippy. So an array is specifically defined in a trie, usually, as having a fixed number of characters, a fixed number of buckets, namely 26. Or in fact, in the P set, you'll see 27, because we allow words to have an apostrophe for plurality and so forth. So let's suppose, though, for now, that each of these arrays is of size 26, or maybe 27 for apostrophes. So what does it mean to store a dictionary inside of a trie, a data structure like this? Well, this happens to be a picture from a textbook that was implementing a trie for people's first names. And notice, even though it's not obvious at first glance, here's the root node of this trie. And notice what each of the elements in the array is actually meant to do is it's meant to represent a pointer to another node. So even though we've written in this picture letters of the alphabet, you can think of A as just mapping to bracket 0, and B as mapping to bracket 1, and Z mapping to bracket 25, and apostrophe, who knows where. You'd have to special case it, but somewhere specific. So what really each of these elements in a trie's node represents is a pointer to another such node. And so what you do with a trie is you implicitly store words as follows. If I want to insert the name Maxwell into my trie, I first start at the root of the array, the root of the trie. The trie initially has nothing in it. This is kind of later in the story. Initially, the trie just has a single node with a whole bunch of null pointers. But I want to store Maxwell into this trie. So I look at the value of M, which is 13, which is the 13th letter of the alphabet. So let me subtract 1 for 0 indexing and 12. So I go to bracket 12 in the root nodes array. It's initially null, so I use malloc, and I allocate another node. That's going to be this node over here. And I attach a pointer to location 12 that maps to that new node. Now, I haven't put the letter M inside of the trie's node. I've just implicitly assumed that M is the 13th letter, which means bracket 12 if 0 indexed. So its pointer means, you know what? There exists a pointer here because there is some word in this data structure that starts with the letter M. So it's all implicit. And this is what's pretty neat about this. Now the story continues. The next letter in Maxwell's name is A. A maps to the first letter of the alphabet, or bracket 0. So I initially say, all right, give me another node. So I use malloc to instantiate another node of pointers. And then I hang a pointer off of bracket 0, pointing at that new node. And now for space efficiency, notice that the author of this book did not draw all of these nodes out. A trie is interesting that it's a very bulky, wide data structure because you have all of these arrays. So he's only showing you the letter that's actually relevant. But if you continue this story, what a trie really is, it's a multi-layered hash table where you initially hash on the first letter of the word, then you hash again on the second letter of the word. But the hash function is really simple. It always returns 0 through 25, which tells you what the number is in the array that's supposed to represent that character. And then once you get down to LL in Maxwell, it turns out that you need a special marker in your structure that says word stops here. But in the end, what's neat about a trie, and it's a tricky one to wrap one's mind around the first time around, what's neat is that you're not actually storing any words per se in the tree. It's all implicit. It's a huge data structure full of pointers, not actual content. But here's the magic. What then is the running time of search on a data structure like a trie? Hash table, recall, was big O of n divided by k, but k is a constant, so it was really big O of n. What's the running time of search on a trie? It's big O of Like, well, we need a new expression here. Let's call it m, where m is the length of a word. Notice to find if a word is inside of the try, you have to hash on that word's letters, M, A, X, W, E, L, L. So it looks like the running time of this is at least 7. Now, maybe if it's David, I'm inserting D-A-V-I-D. Ooh, looks like the running time of a try is actually 5. But the point is, it's some constant. And if the constant is defined as longest word, the running time of a try's search function is maybe 10 if that's the longest word in the dictionary. Maybe it's 20, maybe it's 40. But it's not dependent on n, which means you could have 1 billion words in the try. You could have 1 trillion words in the try. And you know what? You can still find David in 5 operations, D-A-V-I-D. And that's what's particularly magical about this data structure. If you spend, frankly, a ridiculous amount of RAM, because the structure is pretty wide, you can get truly constant time lookups dependent only on the length of the input, not on how many things you're inserting. So the challenge for you for problem set 6 will be to choose from among those data structures and implement the fastest spell checker possible.